Right. Before we begin, I'd like to acknowledge and pay respect to the traditional owners on the land in which we meet, the Gadigal people of the Eora Nation. It is upon their ancestral lands that the University of Sydney was built, and I'd like to pay my respects to their elders past, present and emerging. Hello and welcome. My name is Katrina Liberia and I'm a curator here at the Chau Museum. I'm delighted to welcome you here tonight for our National Science Week lecture, Study in Visual Perception, or the Art and Science of Visual Perception, given by David Alais, Professor of Experimental Psychology here at the University of Sydney. David studies how the brain uses images and sounds to build a perception of the world around us. He spent a decade overseas in the US, France and Italy, working with world leaders in the field, and now heads a multi-sensory research group in Sydney investigating vision, touch and hearing. His work explores the ambiguities of perception, the limits of awareness, and the role of inference and prediction in what we see. He's fascinated by the way art can reveal the visual brain at work and show the fundamentally interpretive and subjective nature of vision. Before I hand over to David, I will provide a very brief biography of the artist Lily Greenham, whose work Study in Visual Perception, currently on exhibition downstairs on level 1 as part of our artist project Consuelo Caverniglia, Seeing Through You, the work is the basis for this lecture. Lily Greenham was an artist, performer, composer and leading figure in sound and concrete poetry. She was born in Vienna in 1924, where her early life was shaped by her Jewish Polish parents and the events of the Second World War. Following the annexation of Austria in 1938, Lily, aged 14, was evacuated to Denmark, where she joined her mother and stepfather. Lily's father was taken to the Buchenwald concentration camp and remarkably later released, fleeing to Shanghai. For Lily, her new life in Denmark was short-lived, and following the German occupation, her mother was shot and killed while attempting to flee to Sweden. Lily survived and found refuge in Sweden, where she lived until the end of the war. This upheaval was to be a constant theme throughout her life. In the late 1950s, she returned to Vienna to study at the Academy for Music and became associated with the Vienna Group, an experimental theatre group for Austrian poets and writers. By the early 1960s, she had relocated again to Paris, reinventing herself, and became involved in the lively experimental opkinetic art scene centred around the legendary Parisian gallery Denis René. It was during this period that she made Study in Visual Perception, a two-coloured opkinetic collage of fourfold rotational symmetry. Each section is a mirrored image in both directions. The artwork has a separate lighting program of white, red, yellow, green and blue light. Lily was involved in op art and kinetics between 1963 and 1970, and she was included in many influential exhibitions at the time. The Responsive Eye at the Museum of Modern Art in New York in 1965, Light and Movement at the Musée d'Art Moderne de la Ville in Paris in 1967, and Kinetics at the Hayward Gallery in London in 1970. After short periods living and working in Madrid and Lisbon, she moved to London in 1972 and made a major return to experimental music and coined the phrase lingual music to describe her text sound compositions and her grasp of 8 languages. In 1974, as a guest of the BBC Radiophonic Workshop, she created her best-known sound work, Relativity. She died in London in 2001. I'll now hand over to David. If you could please make him welcome.
Thank you, Katrina, and thank you, everybody, for being here tonight. It's a real pleasure for me to talk about two things that I really like a lot, which is my work in visual perception and visual art. And so while you've been sitting there, you've been watching the artwork. It's a kind of dynamic piece. It's actually that tool now, it's on whiteboard and it's got a whole lot of little mosaic pieces, kind of like a collage on top of it. And the artist described a very particular pattern of illuminations that needed to be shone on it. And what I'll be talking about today, one of the things I'll be talking about is how that affects the things that you see and picking up on a few interesting phenomena. So once I was asked to talk about this artwork, the more I looked at it, the more fascinating things I found. So what I'd like to do, first of all, is begin with an overview of what we mean by perception and actually how we perceive the world, and alert you to a bit of weirdness. For example, we don't really see what's out there and we mostly build it in our heads. And of course, the fact that we build things in our heads without it directly corresponding to reality necessarily means there's a lot of ambiguity and a lot of scope for artists to play games. And I think Lily Greenham is probably really an amateur scientist. She clearly thought long and hard about these things and created some great effects, which I'll get on to. So I guess in a nutshell, my field of expertise academically is perception. And I should stress by that I mean sensory perception. So through our senses, we perceive the world outside. And I know perception has another meaning. I not so long ago was talking to a fellow who turned out to be an important businessman, and he asked me what I did. And when I said I was a professor, he said, "What do you study?" I said, "Perception." And he said, "Oh, in my field, perception is very important." I said, "Really?" He said, "Yeah, I go to a lot of important meetings. I always wear a good suit and polish my shoes because perception's everything." And I said, and I totally agreed, perception is everything, but clearly we meant different things about perception. So I'm definitely talking about sensory perception. So there's a world out there. How do we know the world? It's mediated through our senses. And as that image sort of conveys, you're not necessarily seeing the world as it is. You get a limited sample of information and you construct the rest in your head. And so the key point is then we don't know the world directly. There's a sensory interface and the world is on the outside of that interface and our conscious experience is on the inside. So somewhere in the brain, through touch and taste and smell and all the senses, we develop a sense of the world, subjectively in our minds. And it may or may not correspond to reality. So we can ask the question, do we really see what's out there? And there's many ways that you can show that that's just not true. I mean, in the simplest case, you're familiar with how cameras work and the little pinhole rays cross over. So in fact, the image that lands on our retina that guides our perception to begin with is upside down and left-right flipped. So no, it doesn't really correspond to what's out there. And there's actually a lot of stuff that we don't see. So visible light is actually just electromagnetic radiation. They're just radio waves. Just like when you listen to the radio in your car, perhaps driving along, those are radio waves driving the radio. They don't have colour. If you've ever had an X-ray, you don't get a burst of colour when the X-ray machine's turned on because electromagnetic waves have no colour. But there is a narrow spectrum within the middle of that band where subjectively in our heads we create colour. So most definitely the colour does not exist in the world. It's not even in the light waves. It's literally invented in the head. And so do we really see what's out there? Well, no. And there's a whole lot more you could be seeing. So humans and insects, for example, see different parts of that electromagnetic spectrum. So a human might see this flower as a beautiful yellow flower, but an insect who has ultraviolet sensing will look at that and see it as a two-toned flower. And, the insect image highlights the centre of the image because a lot of insects and birds want to find the centre of the flower where the pollens and things are. So it's very functional for them. At the other end of the spectrum, you have animals like snakes that see infrared light, which we can't. So they see things that we can't. At night time, they'll see mice, for example, and of course we can't. And so, there is this very limited band of light that I've shown there on the right. And insects are seeing down this end, ultraviolet, and reptiles are seeing at this end, right? And as I think most of you know, there are these three sort of colour filters that live on our retina. We have photoreceptors, light receptors on our retina that come in three varieties that respond either to the short wavelength light, the medium wavelength, or the long. And in your mind, that corresponds to blue, green, and red. So you're not seeing everything. You could be seeing more. This applies to all the senses. So if you consider other animals, And other senses, we hear up to about 20,000 hertz. That's if you have pristine young ears and they haven't listened to too many earphones and loud music and industrial noise. You might hear as high as 20,000 hertz. And bats, of course, hear over 100,000 hertz, and your dog is hearing at least twice as high as you are. So they're hearing things. You might sit there and not notice the sound, and the dog might prick up its ears and hear things. So we really are seeing a subset of things because it's a filtered world. It comes through this filtered sensory apparatus, and ours might be different to another species, or indeed within the same species, though within the same human species you can get abnormalities. So there's a beautiful red flower simulated to have all the RGB, the red, green and blue colour in it. But some people are colourblind, meaning it's not that they don't see any colour, but most usually they don't have the long or they don't have the medium channel. So they always have the blue generally. It's very rare not to have that. It's either you miss the medium or you miss the long. And of course, perception is mediated through this sensory apparatus. And so you will have different colours if you're colourblind to what the rest of us will see. So if you're missing the long wavelengths, the red looks like that. If you're missing the medium wavelength, it'll look like that on the bottom. And in very rare cases, people are missing the short wavelength cone. And then things go really red normally. Now, I mentioned dogs before. I'm very fond of dogs, but unfortunately their colour vision is quite limited. Other species, we have these 3 channels, as I mentioned. Dogs only have 2. They have a yellow band and a blue band. And so their range of colours is like what you see there. So if you buy your dog a beautiful red bowl, dinner bowl, the dog's really not appreciating it. It'll just be grey to the dog. Or a deep royal blue, the same thing. There's even an animal called a mantis shrimp that has about 10 or 12 colour channels. So I can't begin to imagine what sort of a colourful world they see. So I made the point that perception is subjective. It's created in your mind. Well, everyone understands, I believe, you've seen this image a million times, a beam of white light, it could come from a light or it could come from the sun, can be shown to be composed of these components. So when the light ray goes from air into glass, which is a denser medium, the rays bend. And because there's a range of frequencies in there, what range of wavelengths, they bend by different amounts. So all the colours fan out beautifully. And you can see the different colours, as Newton showed about, 4 centuries ago. So light is composed of all these different colours, only that's not really the case. I did stress they are wavelengths, they are not colours. That's what you would perceive, but it's not in the actual signal. And so how do we see? So we see through reflected light. And that's one of the keys why I said we don't see the world out there as it is. It's not like, we use vision as a kind of active verb. I might say you can look over there as if you can somehow cast your vision over there and apprehend what's over there. But of course you can't. You are just receiving reflected light like this. The sunlight lands on this leaf. It has pigments in it that might absorb all these colours except the green one. So the green one bounces off into your eye. And so you think the object is green. That's the intuition. It's actually incorrect. It's more like this, in fact. Sun emits electromagnetic radiation, a range of frequencies, and they're not coloured. So what's hitting the object itself has no colour, as I said before. X-rays have no colour, radio waves. And then certain of those wavelengths get absorbed, but a small band is reflected to the eye. Once it enters the eye, on the retina, as you know, there are red, green and blue sensitive photoreceptors. Well, I even said that right. So easy to fall into this trap. You have photoreceptors sensitive to short and medium and long wave light. And so the colours are in your head. The physical reality is just a wavelength that has no colour and an object that has no particular colour either. That's constructed in your head. And so I might tell you to look over there, but of course all you're doing is passively turning your eye and capturing signals from there, and then in your head computing, what could it be over there that gave this pattern of light on my retina? And you don't actually know the answer. So it's a guessing game. And current theories of perception suggests that actually most of what you see is a prediction. You don't even, we have the intuition that we open our eyes and there's a live stream of information coming in and we churn through that like a graphics processor and out pops a sense of vision. It's actually not like that. The current theory suggests that we've got such a robust model of the world, we've got so much experience that we can almost predict what we should be seeing. And often we prefer to predict rather than see, because seeing, if you just churn through all that information, seeing is the biggest thing the brain has to do. About 30% of the brain is dedicated to vision. And if it was churning non-stop because you wanted a continuous live stream of information, there just wouldn't be enough brain capacity. So better to have a robust model of how the world should be and predict. And so the current theory is you predict what you should be seeing, and if the input coming in matches the prediction, you just stop processing there and say, I've already got this, I don't need to churn through all that processing. So it's a reflected world. We don't directly know it, and in fact, most of the time, we're guessing and predicting. And so the point then is that perception is an active inference. You don't know what's out there, but you actively try to infer it. And you try to see patterns and you try to get to the bottom of what's on your retina. So if you look at that, you might see a cube in there, yeah? If you piece those lines together, there's kind of a cube. So we're very good at finding structure in amongst elements. So we group that into a cube. You might see a face in here if you look carefully. About 40% of people report seeing faces in here. Did anyone see a face in there? No? Kind of. 30 or 40% of people report seeing it, but there isn't one in there. There is one in here. But it's interesting because the brain's trying to predict what it's trying to make sense of this massive visual input, and it's got some particularly common templates that it's used to, like getting face type information. So it even mistakes sometimes seeing a face there, even though there isn't one. And of course, your brain is so adept at applying templates to try and see things that it might even see like an angry face in a handbag like that. And that phenomenon you might have heard of is called pareidolia. And you might see faces in clouds, in handbags, in all sorts of things. So we're actively trying to interpret what's on the retina because we don't actually know what the real situation is over there. So here's an example of active inference at work. So you have an image reflected onto your retina, but you don't necessarily want to base everything on what reflected to your retina. You'd like to try and guess what's the situation out there in the world that caused that reflection. So here we have an interesting image. We have sort of like a folded three-dimensional shape that seems to be pointing this way. There's a ground plane, we've got shadow, and this appears then to be in the light. There's a shadow, and this surface appears to be in the shade. So this is a very dramatic illustration, but the top grey and the bottom grey are the same. You might even put your hand like this and obscure that border between them, and you might see they're almost the same colour. Yeah, it does work, and I've actually chopped a tile out of each one, and you can see that they're the same in isolation. So what's going on here is that at some point on the retina you get this grey image, and at another point you get the same grey image, but the brain's trying to go further to interpret what in the world might have caused this. And given the structure and the apparent shading, the brain's going, wait, they're the same luminance, but one's in darkness, one's in shade. So if something is equal on my retina, that it's in the world being darkened, it must actually be super bright in reality to equate one's darkened to what's on my retina. You can see what I mean. So, and it's not just shades of grey. The brown and the brown and the orange shades are exactly the same colour. It's the context, the shading that makes you think they're not. If I zoom in a bit, I don't know if that helps. They still look very different, don't they? But if I, again, cut out a segment, you can see they really are, on their own, identical colours. That one's the same as that one. And the brain goes, well, if that's the same as this guy, but obviously this guy's in shadow, so if I were to try and explain it in terms of what's happening in the world, this must be super bright in reality. If once shaded, it looks the same as this guy. So this is this active inference thing going on. And so the takeaway from all this really is that your brain's kind of a virtual reality machine, right? We don't really know what's out there, but we simulate it in our minds, right? And so, you can put on a VR headset and have virtual reality, but that's really like VR on top of VR. Your vision's already a kind of VR. This is like VR squared or something like that. You're simulating the world. But of course, it's not just a random simulation. It's guided by evidence and experience. And so it's actually, in that sense, a bit like artificial intelligence. AI, as you know, is very topical and is all through the papers and things, and people are worried about, is it a good thing or a bad thing? But it's an incredible thing, make no mistake. You can take a deep neural network and you give it some input, even a text input, like create a face. And all these cells churn away and out comes a face. Meet George. That's the output of the network. And you think, surely that's not possible. Is it really? But of course it is. So here's 4 faces generated by AI. These people obviously don't exist. They were generated by a computer program. And there's even a website there you can go to. You see, it says thispersondoesnotexist.com. If you go to thispersondoesnotexist.com, a web page opens up with a brand new, freshly invented face out of a neural network. And every time you refresh the page, it spits out a new image. And there's lots of studies that show that people cannot tell the difference between these computer-generated faces and real faces. So AI is kind of like human perception in that they both rely on highly trained models. So, I said before, current thinking is that we've got such a large store of information in our heads that we've got a good model of how the world is and how it should be. So you have a good basis on which to predict. So it is VR that we have in our minds, but it's guided by some pretty solid models. So just like AI is guided by models. Now, AI truly is incredible. You can ask AI to do anything that's been trained. So that you've all heard of ChatGPT that can write text for you. It's also highly trained. They literally scraped off every piece of text they could find on the entire internet and trained a network to predict the following words, given a prompt. And after scanning every text on the web, it got very good at that. I asked ChatGPT to write me a haiku poem because I love haiku, and it just immediately gave me this. And that's a beautiful poem in the haiku format. And then I got carried away and I thought, can you write me an ode to Lily Greenham? And this one's a bit cheesier, although the first line has a stunning alliteration. In the fields where daisies softly sway, Lily Greenham dances bright and gay. With laughter like a springtime breeze, she paints the world in vibrant ease. Now that's a bit cheesy, I think. I like the first line alliteration, but still I'm impressed that it could give me an ode to Lily Greenham. So that both ChatGPT and face generations, they're highly trained networks. A friend of mine who's a world expert in detecting fake videos and images, and does a lot of work for the US government on this, told me that this is a very old technology, this one here, but the latest face generating things were trained on a database of 8 billion faces. That's a B. And I said, wait, that's more people than live on the planet. He said, yeah, people have multiple photos, some of them. So 8 billion photos, and it was trained. So they're highly trained and create incredible things, but we have a highly trained brain too, so we create equally amazing VR in our minds. Now, that brings us to Lily Greenham. So I was asked by Craig and Katrina if I would speak to this painting, installation. I went downstairs and looked at it, and by the way, it's on the bottom floor here, and some of you may have just responded to the advertisement and come for the talk, but you can see it downstairs. I don't think tonight because it's closed, right? But you must pop back and see it live in the flesh. It's a beautiful thing. So I studied this and I thought she was clearly an artist interested in science and the science of perception. And I tried to pick out all the different things that she had touched on as a kind of amateur scientist that leapt out to me as being really instinctive scientific observation. So I came up with a list of things, and I'm going to go through each one in turn. And we'll start with the role of illumination, because she specifies very clearly what the projecting light should be. As you can see, it's changing. So what does that tell us? So there it is in white light. It's a white background with these little colour tiles on. Most of them are coloured in two colours, the colour tiles. There's green and magenta. And so I've zoomed in there so you can see what they look like. And it's like a mosaic artfully assembled to create different kinds of shapes and things. But what is she doing with the illumination? So when it's in yellow light, it looks obviously quite different, because you've now got yellow light reflecting into your eye and interacting with the existing colours. We see that the magenta that was in the centre of these chips goes orange, and the green, well, it just goes to a darker green. So green goes to green, but the biggest change is that magenta goes to orange. Now, that, of course, makes perfect sense when you look at the colour wheel. So here we have, of course, all the visible wavelength spectrum wrapped around this circle. And in the white outline, these are the basic colours that you see in the unlit or the white lit environment. So we've got green and magenta. So what happens when you add yellow light to green and magenta? So the colour wheel, if this is an art audience, some of you will know this, of course, but on a colour wheel, you can predict what the sum of the colours should be. You take 2 points anywhere on the colour wheel, and if you sum those lights, you draw a line between the 2 points, and the middle will be the sum of the lights. So based on that, the green part of the tile, when you add yellow to it, there's our straight line. That should be the average. So green plus yellow should give, well, another shade of green. And we did get a shade of green. The interesting one is the magenta. When you add yellow to the magenta, there's the line, and the midpoint is clearly red, orangey red, yeah? And that's what you get. So no doubt she knew this, and she was playing with the illumination to change the colours. And then she adds cyan light. And so if you take the magenta tiles and you've added a cyan to it, you end up, the average is there, so a nice dark blue. And look, it's beautifully dark blue. And the green, well, it just averages to another shade of green. So you get this slightly light shade of green. But the interesting one is red. She's done something very clever here. When I drew these diagrams, I thought, oh, now I see what she's done. So we've got green and magenta, and she's added red light on top. And so there's the average, a kind of a dark red. Magenta goes to dark red, of course, as you see. But look at this. Green, when you add red to it, you get a point in the middle. And the middle of the colour wheel is either, well, it's achromatic. Because those colours, I perhaps should have mentioned this, but the edge of the colour wheel is completely saturated, and you add more and more white, and it's the same colour. It's just getting whiter and whiter, and in the centre of the colour wheel, it's achromatic. There is no colour. It's just black or white or a shade of grey, depending on the illumination. And so now, do you notice, all of these tiles had 3 colours in them. Well, there's a background plus 2 colours in the tiles. Now here there's a background plus 2 colours in the tiles. Now that she's added red light, it's achromatic. We've only got 2 colours all of a sudden. The red background and this sort of black colour. That's, achromatic right there. So it's now a 2-tone pattern instead of 3. So that's pretty cool. That's got to have been deliberate. Now, artist come scientist, Lily Greenham. So I showed you that before. So there's just looking at the colour summation in the colour wheel doesn't explain everything, because colour's a bit of a strange thing, and there's other things that go on. I showed you that. Here's another example, by the way. You see there's a green tile and an orange tile in the middle, but they're actually the same colour. If I take away the surrounding, they're both green, right? And that's called simultaneous colour contrast. And we see something similar in Lily Greenham's painting. Look at this. The tiles under the cyan light, these ones look yellow, but if you take them out of context, you see that they're actually green, which was the prediction from the colour wheel. But they go kind of yellow in the context of everything else. So many artists have known for a long time you can't always get the colour you want on a painting because the ones around it influence it. That's a classic example. Here's an interesting thing. So what the brain's trying to do when it creates colour, it's trying to guess what the true colour of the object is out there in the world. And it does achieve this, and it achieves the process is called colour constancy, is the term for this. But probably what you're seeing here is a bunch of red strawberries on a plate. It's actually a red strawberry cheesecake. And they do look red, don't they? However, it's actually grey. And if I had the time to, perhaps afterwards, if people are interested, I've got this set up in Photoshop so we can use the colour clicker to find out exactly what shades they are. These strawberries really are, on the screen, not in your head, on the screen they are absolutely grey, and I could demonstrate that. But you also notice it looks like there's a blue wash over the whole image, right? Even the wooden tables seems to have some sort of blue offset to it. The plate's kind of bluish. Everything's a little bit bluish, and so the brain goes, this must be an illumination that's blue. That's biased the entire image towards blue. And so the brain subtracts the blue. And in subtracting blue, where's my colour wheel? There. If you have an image that's achromatic in the centre, and you subtract blue from it, you'll drift, it was a light blue. But here, if you subtract blue from that image, you end up drifting towards red in your mind. And that's what indeed happens. If that's not clear, don't worry, I could demonstrate that, but we will move on, because this is another form of colour constancy that a lot of people have seen. This is the dress that broke the internet. A lot of people see this as a black and blue dress, don't they? Any black and blue people? Yeah. But some people see it as yellow and gold, right? Yeah. So I see it as yellow and gold too. But why do people split down the middle on this? It's because of this thing called colour constancy. I told you at the beginning, the colours you perceive are the colours that reflect off objects and into your eyes. So that's all very well, except that if you change the colour of the illumination, you're going to change what's reflected into the eye. And that's misleading. The brain would really like to know a true and stable colour. So any time it thinks there's an illumination bias, it subtracts it out, so that you arrive always at the true colour. The problem here is there's a real ambiguity, and ambiguity is a problem for perception and a great thing for art, but a real problem for perception. What am I seeing? Is this the dress indoors in artificial yellow light, or is it outdoors in daytime where the light's more bluish? I need to try and work out what the illumination is and subtract it so that I always see the true colour. But which assumption should I make? The people who see it as blue and black are assuming that this is taken in interior light that has a yellow bias usually, and so if you subtract that yellow bias, things shift towards blue and black. But there's other people, and I'm a gold and white person, I never see it blue and black. I must be assuming that this is shot in the outdoors where light is blue biased by the sky, and if I subtract blue, then it shifts more towards white and gold. So actually, the fact that people split down the middle on this is interesting. It shows that everyone is making assumptions about what they see, and on limited information, you might opt for one assumption or another without much evidence and just totally change your perception. In truth, the dress is actually black and blue, and the story is quite funny. A woman was buying a dress for, I think it was a wedding, and she saw a dress she liked, took a picture and sent it to her friends and said, I found this wonderful black and blue dress. I think it would be great for the wedding. And then a bunch of friends wrote back and said, no way, it's white and gold. What are you talking about? And then the other half of the friends said, no, it is black and blue. What are you talking about? Anyway, it went online, and as you know, it went totally viral. So it's kind of a funny story. But it does reveal that the brain always is trying to assume more than, what's on the retina to try and find the truth. Two more things I can tell you about Lily Greenham. So we tend to think of the visual system as a unitary thing, but it has two subsystems. One that's sensitive to colour contrast and one that's sensitive to luminance contrast. And vision works just fine with luminance alone because black and white photos are just fine, right? But of course you can add colour too. So if we look at her painting on the left, we can consider which of the two subsystems is active here, the colour contrast or the luminance. So when it's in the natural light there is only colour contrast operating, the green and the magenta. And I can tell you that there's no colour contrast in those tiles because when I make them black and white, they all look uniformly grey. That centre surround structure, there was a clear centre surround on each of those colour chips, and it's essentially missing on the black and white version. And of course, black and white, it's just differences in luminance that you're seeing. If the tile looks uniform, there was no luminance contrast. So here we have no luminance contrast, no colour contrast, just the spatial structure. If we look at this one, for example, this one does have luminance contrast because if I make the image black and white, I still see the tiles have their individual two-tone property, right, which you didn't see here. So that does have luminance contrast, and of course, obviously, it's yellow and blue and has colour contrast as well. So I feel like she was playing games with many aspects of colour vision in this image. And then the different colourings, one of the things you really notice is it brings out different structures, right? And organising elements into forms and shapes and wholes is one of the things that the visual system's always trying to do. It's trying to make sense of these strange patterns of light on its retina. So it's always looking for patterns. But sometimes there's ambiguity, of course. So there's that cube figure I showed you before, and that's what it looks like without the discs on it. There's millions of examples of ambiguity in vision. So is this a vase or is it two faces? If you stare at it for a while, you'll be convinced it's a vase and then flip to two faces. But, have a look at this video on the right of Albert Einstein. So trying to interpret the retina is really difficult, and sometimes their assumptions are wrong. So there it's clearly rotating round to the left at the back, but then it comes back the other way. It's actually truly rotating constantly in the same direction. It's a concave or convex, in which side you're looking at. It's a moulded image of the face. But you always see faces convex towards you. You never see them concave. And so as soon as it flips to the back and you should be seeing the hollow side, you just immediately, faces are always concave towards me. You can't see it any other way. So you should be seeing it the other way, but it's another example of the assumptions your brain makes, just like it tries to assume the cover of illumination. So ambiguity, the search for patterns, is a thing that is inherent to vision. And so there's more than patterns than this in this image, but clearly you see a kind of a circular form at the top, a diamond shape in the middle, another circle at the bottom. If you change the illumination, you see different patterns. Actually see at the top more of this sort of a shape that I'm not aware of in the top left, in the green and magenta. In this, you see a different kind of pattern again, which you're not aware of so much in the others. And the red one, you get these really strong, clear diamond shapes. And I was making this slide last night, and it suddenly occurred to me, wait, there's also a square in here. The more I stared at the red one, I saw a square in there that I couldn't stop seeing once I saw it. This is very cool. Your brain's always kicking away trying to put the pieces together. What's the whole that I should be seeing? And she's playing games with the illumination, and you end up putting it together in different ways. So that's very interesting, I think. If I have time, do I have time? What time is it? I think I do. Yeah. All right. I'll go on just very quickly to talk a little bit about the brain and vision. So since we're in an art space, looking at art is actually really good for your brain. Your brain, I talked about the ambiguity that we sometimes highlight in visual perception because that reveals the limits of perception, but of course then that's fertile ground for artists to play with that, because when you see ambiguity, you stop and look a second time. We predict the world, as I said, and we do have these highly trained models like AI in our heads. So we can usually pigeonhole everything that we see really quickly. But when you go into an art gallery, you walk past something and, oh, wait, what is that again? And you realise it's ambiguous, and you stop and interrogate it and have a second look, and it sets you thinking, and is it something I've seen before? What's it like that I might have seen before? That ambiguity is one of the great things about admiring art. And there's a part of your brain that absolutely loves that sort of ambiguity. And I'll illustrate that on the next slide, but that's the inner, the brain's made of two hemispheres. So if you split them open and look on the inside face, there's the structure on the inside of the frontal lobe and here as well that are very active when you're in a reflective, inwardly focused, contemplative mode. And just very quickly, it's called the DMN, the default mode network, a massive network in the brain that people didn't know about until about 10 years ago, believe it or not. It's now a really hot topic of research. But you've seen all these images of brains with hotspots of activity. The areas that you see there are the sorts of areas that light up when you're busy doing a task, consciously applied to a well-trained task, right? Writing a report, doing some figures in Excel or whatever. And when you switch off and let your mind wander and reflect inwardly, a totally different network lights up. So that area is not active here. This area is not active there. And these parts here also. So completely non-overlapping part of the brain lights up. And interestingly, they discovered it only recently. Vision neuroscientists are forever putting people in fMRI scanners and seeing what parts of the brain light up when they do different kinds of tasks. And one day someone had the bright idea to put someone in a brain scanner, plug their ears, cover their eyes and say, do nothing, think nothing. And they thought the brain would just shut down with nothing to do. And instead, it lit up like this Christmas tree. And that was the discovery of the default mode network. And no one believed it for a long time, but then everyone started to find it. And it turns out to be a thing where when you reflect inwardly, it becomes active and it interrogates your sort of maybe your life history, your memories, your thoughts. You contemplate, you reflect, and that's the part of the brain that lights up when you look at art. Art that you like a lot lights it up more. So you can see these areas, and this one in particular, are much more lit up here when it's art that you've rated highly. So it's not just any art, it's art that particularly engaged you, which makes sense. They're the ones that make you stop and think. And this other part of the brain lights up, and it's kind of relaxing because that other network I showed you is the network that lights up when you're busy doing tasks. Well, enough of that. Sometimes you need to switch off and relax. And it's very relaxing when your DMN lights up because suddenly, instead of being responsive to external stimuli, you're internally driven. And it's much more relaxing. And so, going through an art gallery, just looking at art books, even wandering through a forest or something is also very effective at activating this network. So why do we find things attractive in art? Aesthetics can be very particular, but it can also be something common. Do we have a common sense of beauty? Well, there's lots of things that are universally admired. Does that mean we have a common aesthetic? Well, people have looked at this for colour, and since Lily Greenham was a big colour enthusiast, obviously, I thought I'd just share this with you. Here's a painting of Picasso with a colour wheel. And since this can all be digitally represented, you can play some interesting games where you can take that colour wheel and you can just rotate it by 90 degrees, right? So, there's a red. Well, if I turn the wheel 90 degrees, I'll substitute green for red. That cyan for this green, and that magenta for that. You could rotate the wheel and it would look like this, all right? So it's the same image. We've just, in a digital way, rotated the colour wheel, plus 45 degrees, minus 45, minus 90, and the image totally changes. And the very cool experiment was done where they showed people these images, and they just had a knob they could turn, and they said, here's a painting, and most people had never seen these paintings before, just that knob until it looks nice to you. And so invariably, people turned it back to the 0 point, the starting point. So they're all different images, many of them they've never seen before. But that's a distribution, if you like. That's like, I don't know, there's a few hundred people in there, That's actually a distribution, if you see what I mean. And the peak of the distribution sits over 0, meaning, it had been turned 45 degrees left, and people adjusted it and they set it back to 0 where it was. And that's what they preferred very much, as you can see. So, maybe we all do have a preferred aesthetic, and clearly these are paintings that don't have any predefined. It's not like the apples need to be red and bananas need to be yellow. These are abstract and could be any colour. And yet there's a kind of harmony that people like. So who knows? Maybe there is a commonality in aesthetic beauty. And I think this is my last slide. Not just art appreciation is good for activating that inner network that you have doing art. So these people trained in art just for a 10-week course, and there's their brain activity at the beginning and the end and the change. And what you notice is that those who actually made art grew significantly more activity in this medial prefrontal cortex. That's part of this DMN network. And in the PCC, the posterior cingulate, which is also part of it. And you get a little bit of that change if you just, look at art and evaluate it. But these people were basically told to evaluate it sort of logically and critically, whereas other people were actually making it. And it seems like the logical evaluation doesn't quite do it. Doing the art really does. So I think I've said a lot. We're out of time, but I'm really up for a host of questions. So please, any questions, I'm happy to take questions as long as people still have questions. Thank you very much.
Is there any endeavours in how the brain makes decisions? Can that explain why you can't concept goes?
Does that explain why women can find things? Yeah. And then, I know about that. It happens to me all the time in my house. There are some differences, a lot of the basic functions of perception are pretty much common to all of us. But, there are definitely different, at a higher level, I'd say different cognitive ways of thinking. And, I'm definitely the impulsive one that I go and look for something and it's not there and I start complaining that I can't find it. And my wife invariably says, it's right here. So I know what you say is true from personal experience, but I'm not actually sure what the explanation is. I know some researchers have identified cognitive differences between males and females, but it's not quite my area.
I'm just wondering about the practice point. So you said it could deep into the MRI machine and ask them to basically not think about anything. But when you're looking at art and evaluating them, you're actively thinking about something. I'm just wondering how that activates your
So, that's a very good question. The DMN, it stands for, I'm sure I put that up there somewhere, default mode network. So it's like the brain will do things for you when you apply it to a task, or it will respond to stimuli outside, but by default, it's always going to be operating. That's the idea. So if you give it no external input and you stop thinking about it, it will just spontaneously start activating. So by default, there must always be some activity, but it's a different network. Often if you're sitting really quietly and you've relaxed and switched off, your mind wanders onto all sorts of topics, and that's your default mode network. You can't, perhaps if you've done, a deep meditation session, you might find your mind's gone really quiet, but in general, moments of quietness where you turn off the external stimuli, your mind wanders. So it's a default thing. It must happen. It's like that energy must keep circulating somehow.
Thank you. I was just wondering, when you're talking about assumptions that we make, I presume a lot of that is not innate for plants, so, a baby's perception of the world is also different in its growth. So I was just wondering about
that's true. So there's no doubt that's the case. I would love to be in a baby's mind. I wish I could transport myself in there and experience what it's like. when babies are born, of course, they're effectively blind. I mean, kittens are blind when they're born. We don't think humans are, but their vision would they be legally blind if you could, call it like that? So at the beginning, they're not seeing anything, and the whole thing's tuned up by experience. And animals that are raised in particular impoverished environments or particular, manipulated environments end up really strong for that environment, but don't see other things. So a lot of it's acquired. I did also say that so much of perception is in the interest of economy, not turning the brain, overworking it all the time, that a lot of the time the brain makes assumptions and makes predictions about the world. It was the point I made with the AI, that AI works because it has super highly trained models, but then so do we. So I've got so much experience with, I've walked around this campus a million times, I can basically predict it. So why would I bother, churning that information anew every time? It is experience driven. That model's in there because of my experience. Assumptions you make, like if you lived your whole life indoors, I guess you would see the dress as black and blue because in your whole experience, lighting's tended to have a yellow bias, right? If you grew up only outdoors, possibly you would always assume outdoor lighting. So it will experience definitely. So it's more than just, it's what I said at the beginning, perception is not really telling you what's out there. There's all sorts of shortcuts and assumptions and interpretations. And so much of that's from experience, 100%.
Thanks. I enjoyed that a lot. So default mode, would that like reading? Because we've taken out all that sort of external stimuli. And so the brain's gone into
they would share some related areas for sure. So the default mode network taps into memory areas very much, and so does dreaming. And so there's some overlap there. I wouldn't say they're one and the same, but definitely default mode network is tapping into memory. So it would be a bit like dreaming, because dreaming seems to be linked to memories. So as much as dreams are sometimes thought to be some extraordinary, tale that we can interpret and find something out of, so often it's just they think these days they're bedding down with memories. And this always happens overnight. So any kind of learning tends to happen overnight. And so things that you've experienced that you want to lay into memory, that tends to happen overnight. So in a totally general sense, if you get to train someone on a task, they don't consolidate the learning until they've slept. And the next day they've learned it. So it happens overnight. And they think that a big part of dreaming is you just activating memory traces that have happened through the day and bedding those down in memory.
in default.
And using some of the areas that you see in the default mode, yes.
I hope we're not.
Yeah, of course.
Isn't the picture of the dress?
Yes.
The first dress I see white or gold, but then you said the dress is really blue and black.
Yeah.
Then you showed the second picture and it's blue and black to me.
Yeah. Oh.
The people who saw the first dress as blue and black, do they see the second picture as gold and white?
Ah.
So is it illumination?
That's a little bit of a fudge. They must have done some. I just presume they've done something to make this unambiguously blue and black, which apparently it really was.
Yeah.
But I thought the same thing. The whole thing's a bit circular, isn't it? I mean, I should be seeing it. That I haven't noticed before, because I only see it one way. But it's possible on the periphery it looks different. I've never noticed that, but maybe a little. The thing that's interesting about this, people are split down the middle. So I did say it's ambiguous. The brain always wants to subtract any potential bias from the illumination to try and find the true colour of the object. So it's always trying to should I subtract interior light or exterior light? It's ambiguous in this case. Could be outdoors, could be indoors. And as I showed you, I'm sure I did somewhere. Ambiguity, it's further on. But whenever there's ambiguity, what usually happens, I can't find it. There was that face bars and the cube flips, right? Whenever there's ambiguity, normally what happens is, if there's two equally likely options, the brain just flip-flops between them in a kind of irregular way. And that cube definitely changes perspective, doesn't it, the more you look at it. This is a rare case of ambiguity where people seem to be locked in to one way of seeing it. I've never seen it other than blue and white. And even though people are divided down the middle about blue versus gold, they never seem to spontaneously change. So it's a rare example of ambiguity that seems to stay locked. So the power of assumptions, I think someone here was talking about that. You must have some powerful top-down assumption that's guiding this. But,
and because we're all individuals who have different, cells, frequency, filters, particular eye, and therefore when it goes to the brain for analyzing, I believe that's how it changes the way we perceive the contrast of information. So even though, like you said, even though the colours, like you said, orange and brown, they're the same shade, but yet you can see different contrast in colours. So that's like the study involved taking into account not just the basic pigments of the colours, but they take into account being a human is an amazing machine. Looking at different layers of cells,
So at the beginning, I think I heard you say, so the eyeball, there's a cornea, and then a lens, and then a whole lot of fluid inside, and then you get to the light-sensitive cells at the end. Worse than that, it's weird. If you imagine my eyeball at the back, there's this hemispherical surface covered in photoreceptors, light-sensitive cells. Cells have wires and fibres that come out of them. The way that eye is rigged up is totally bizarre. The cells on the retina, the fibres project inwards into the eye and have to gather up into a bundle and leave through a hole in the eye. So another weird thing about the eye is that, light has to fight its way through this layer of cell fibres before it even activates the light. So there's kind of a blurring and a shadow before you even get to the light-sensitive cell. There's this layer. And the other thing you were saying was, how do we know that aqueous humour, that liquid in the eye, is perfectly transparent? And light rays that arrive perfectly sharp and parallel, do they scatter when they get in there? And they do. So to some extent, the eye is very clear, the fluid inside is very, very clear, but there's a quantifiable blurring and scattering of light.
And also, I just recently learned that the lens itself, there's a blue filter within the lens. So I wonder if there's anything else, and that's how we can the blue filter in the lens itself.
I didn't quite hear you said we talked about a lens with a blue.
There's a lens, there's some cells in the lens. This is something that I read that it says the lens itself filters out the blue light, especially that sunlight, and then because we have this artificial lighting, it doesn't filter. So there's certain ways that the blue that is filtered out by the lens. They're not all blue light.
Right. Well, it turns out that if the lens did filter out blue light, that's not a big problem because blue is not very important in perception, believe it or not. You have, on the retina, you have about 100 million photoreceptors and about 4 million of them are for blue. And the other 96 million are evenly divided between red and green. Actually, the visual system is all about red and green contrast. and there's a little bit smattering of blue cells. They're important probably because we need to know the time of day, like blue light in the daytime, then it shifts red at night, at sunset, and then it's black. Knowing, just having something that can monitor the changing light levels of day and night helps regulate the body. So that's important for things like, your whole circadian rhythms. But we don't need many blue cells for that. And actually, if I had time and some more diagrams, I would show you that. Well, here, you see how the blue and the green filters are very, very similar, and blue's way over there, completely offset. So because of what I told you, right at the beginning, this where's that image with the, wasn't there a, okay, that's the first one. I thought I had a slide showing okay, there, this one. Because light is different wavelengths, so blue is special, it's off to the side of the other two filters, and that's a problem for maintaining focus because all the light rays bend by different amounts through the lens and through the cornea, depending on frequency. And so if blue was a really prominently encoded colour, we couldn't simultaneously have the blue focus and the red and the green over here. There'd always be a compromise. Either focus red and green and you have blue blur everywhere, or you'd focus the blue and have red-green blur. So the fact that the red and green cells are so close together, where did I put that, means that they both can be nicely focused because they bend by different amounts. So, yeah. Yeah.
There was a landscape painted as you got older. You had cataracts. And cataracts got worse.
Just get distracted. Lloyd Reese, did you say? What did you say? Yeah. Could be cataracts. I'm not sure. But yeah, there would probably be something. I mean, cataracts is a good explanation, isn't it? I think, yeah.
I just want to ask, are you actually working with the School of Arts or the School of Science?
So I'm a scientist, really, and I'm quite fascinated by art, and I love the fact that there are artists that seem to have divined some great scientific principles, but I'm actually science background.
So, as a School of Arts involved in this research?
I have published one paper on aesthetics, but this is a hobby on the side. It's not my research as such, but I did publish one paper on aesthetics. So I got one, yeah. Okay.
So, how did you discover Lily, or when did you discover her, and what?
Katrina and Craig, who here are part of the gallery here, the museum, contacted me. You wrote me an email and said, would you be interested in commenting on this painting? An artist that's interested in visual perception, you must have searched visual perception and found me. And I think I remember writing back, and 2 minutes later, I happened to be at my desk, the email came with that sounds really interesting, yes, I'll be there. All right. So,
we have the Lily Greenham artwork in our collection, research, and we've got an exhibition as part of the exhibition that I curated here. And I'm just getting out to February, so you've got plenty of time. Monday, Friday, 10 to 5, and weekend 12 to 4 to February. And so maybe Google here in university, like we have an aesthetic expert, and I do it. They came up and I was like,
It's fascinating. It's really the same image,
Yeah. And what I'm convinced of now, having studied it so much, it wasn't just random playing. There was something principled behind it. So, yeah, she was obviously very curious and scientifically curious. But I think you were saying her biography, she was very much interested in that interplay between science and art. Is that right?
Yeah, science and art, and music. Yeah. So she definitely consulted, I don't know who, but she definitely consulted somebody in the field of psychology. She was definitely interested in aesthetics, but music as well, and there's a real kind of correlation between the kind of rhythm of music, the rhythm of the collage,
I mean, she did a lot of music, and there's also a lot of science and maths in music. In fact, music is all maths when you get into it. So I'm sure that intrigued her as well.
This is very much from my perspective.
Geometry,
yeah. People who see colour in music, are they seeing a wider bandwidth of vision or
that's a fascinating topic. So that's called synesthesia, right? And synesthesia, colour's particularly vulnerable to being or susceptible to being co-opted into synesthesia because colour is already subjective in your head. It doesn't exist in the world. So you could literally make it up to apply it to anything. It's kind of, it's not a real thing. So it often pairs up with, people, music and colour is one, but gosh, there's every kind of synesthetic combination you can think of has been documented. Some people, read a page of text and every letter on the page has a colour. And for some people, nouns have particular colours. And that's just, and again, someone was talking about, experience growing up and all that sort of stuff. They think that it's linked to that because it doesn't have to, it's not just that, but there's an interesting subset of people who see, black and white text in colour. And interestingly, they tend to see similar colours. There's a subset that do from a certain age group. And they eventually discovered that the American toy maker, Fisher-Price, used to produce fridge magnets, and they only ever made one colour combination. And so you can imagine the little kids crawling on the kitchen floor playing with the fridge magnets, and A's was always red and D's were... But that's not the full story because there's lots of people through history before those magnets existed that had. So it's partly a learned thing, and the letter area in the temporal cortex is next to the colour area. And so it's not a stretch to think that somehow they just get cross-wired. And so an interesting thing, again, about development, the brain when you're born, so you've got roughly 100 billion brain cells, and what's amazing about the brain is the interconnections between the cells. Every cell has thousands of connections with neighbours. And when you're born, the brain is actually overconnected, like everything's possible at birth, and then it starts pruning back when certain things in the world don't reinforce that connection, they just fade away. And so you're probably susceptible early in life to strange associations that somehow get reinforced, like seeing a red letter and that connection's reinforced and maybe that's why. People also grow out of it. My son saw coloured numbers until he was about 12, 10, which I never knew, and that's the other thing about synesthesia. A lot of people don't realise it's a weirdness. I was explaining to my aunt once about synesthesia. She was asking me about my research. I said, well, I've been reading all about synesthesia lately. So my son, who was about 16 at the time, was listening. He said, I just came out. He said, well, you never told me. He says, well, I thought everybody had it. Numbers had colours. And there are people who didn't realise they see coloured objects. Or there was one story I read, a synesthete who nouns in text had colours. And she was trying to think of a word. She was at colleges in the US. She's an adult. She said, what I'm saying, it's one of those orange words. And everyone stopped it. What? And she didn't know until she was about 20 that not everyone saw that object as orange, sort of thing. So it's not like some kind of thing that handicaps your vision. In some ways, it's a benefit. right? I had a research assistant who saw dates laid out in space in front of her. And I thought, that's what I need to help my memory. If I could actually see the, dentist over here and, take the car to the garage here, that would be a great benefit. So synesthesia is a weird thing, maybe due to over connections initially being reinforced. It can be drug-induced as well. So a lot of people know that if you take hallucinogenics, you may have these synesthetic experiences, which then contradicts the idea that it's some abnormal wiring, because it means anybody could be a synesthete if you take the right drugs. So we must all have the capacity for it. Psychedelics is a fascinating topic, and that's for another talk. But it's now a big research area in therapy as well as basic science. Yes, one more.
Just wondering if the vision of that flower might have been by a human. Presumably the same wavelength of light's bouncing off that flower into both of our eyes.
Right.
And yet we perceive that to be yellow, and the bee perceives it to be a different colour altogether.
Yeah, I guess we can't actually simulate. So that's a simulation. Of course, we can't illustrate the ultraviolet because we wouldn't see it anyway. So it's a little bit of a fudge, but it's trying to illustrate that under ultraviolet light that has two distinct regions, and that inner region would be obvious to a bird or an insect, but not to us, even though we can't actually show.
My question is, we interpret that left-hand flower as yellow.
Yeah.
Would that wavelength of light be interpreted by other species other than humans being the same?
So that's that is such a mysterious question. So why? So I don't know, and nobody knows. In fact, nobody knows why a human experience is yellow, corresponding to that wavelength of light. Right? That is completely mysterious. It's as mysterious as, you look inside the brain, there's just brain cells exchanging chemicals and getting electrical spikes. But why in my brain do I have a whole vivid experience of life? Why do a bunch of brain cells create subjective consciousness? That's a total mystery, and so is why the fact that the green leaf was reflecting that wavelength and I perceive it as green. Why not some other colour? Why green? And I think we're similar enough, most of us. We have very similar retinas. That's just an evolved thing that's common for almost everybody. A few, you can be colourblind. There are anomalies, but in general, so the common thing, people say, are you working perception? So when I see red, is it the same as when you see red? So short answer, the uninteresting answer I know is yes. Unless you're colourblind, we would see pretty much the same thing. But I can't tell you why it's yellow, and I certainly don't know what the insect sees. It's mysterious to begin with why it even has come. We're nowhere near understanding that. Absolutely nowhere near. I think we're done. Thanks so much for the questions. I really enjoyed this.